prove part A, and I'm only going to prove like this part of part A, and I'm not going to prove the direct sum in this video. I'll prove the direct sum part in the next video. So here's how this proof is going to look like. Here's the general idea of the proof. To show that one set is equal to another set, we have to show that, so to show that A is equal to set B, we have to show that A is a subset of B and B is a subset of A, right? Now, so we have to show that that this set containing 0 is a subset of this set. Now that's pretty straightforward to show. We don't need to, actually we don't even need rank T equal to rank T2. So for the sake of writing the proof correctly, we first start with our assumption. So assume that the rank of T is equal to rank of T2. Now from this we have to deduce this equality. Now RT and NT are both subspaces. They're both subspaces of V. And because they're subspaces, they will contain 0. So 0 is in both RT and it's also in NT. So clearly 0 is a subset of RT and NT. Now for those, to most of you this might seem a bit trivial or easy, but for the sake of completeness I'm showing this step as well. So 0 is, of course, so this set containing 0 is obviously a subset of RT and NT, and now what we have to show is that RT is in fact a subset, RT intersection NT is a subset of 0. And how do we do that? Well, from if you've done a bit of set theory and you've done proofs in set theory, then you know that we first assume let X be some arbitrary element in RT intersection NT, and then from this statement we have to deduce that X is in this set as well, and X being in this set just means X is equal to 0. Right, so this is how our proof is going to look like. Let me erase this. So let's just call it X. Let X be some arbitrary element in, we write this neatly. Let X be some arbitrary element in this set. So X is in the range of T, and X is also in the null space of T. Now X being in the range of T just means that there exists, so now T is a linear transformation from V to V, right? Now X being in the range of this function simply means that there is some element in our domain, let's call this element perhaps W. There is some element W in our domain such that when I plug W into T, T maps W to X. So what we have here, or X being an RT, can be written as is, there exists some element W such that T of W, I'm going to remove the quantifier just to make things a bit simpler. So there exists some element W such that TW is equal to X. And for this statement, X being an NT, all this means is, well, NT is the null space of T. The null space of T means all those elements that T maps to 0. So X is one of the elements that T maps to 0. So we can write Tx equal to 0. So this is what we have. And what we want to deduce is that X is equal to 0. How do we do that? Well, we know that TW is equal to X, and us wanting X equal to 0 is the same as saying we want TW equal to 0. In other words, we want W to be in the null space of T, right? So we can write this as, so showing that X is equal to 0, is the same as is equivalent to showing that W is a part of our null space, the null space of T, because T of W is equal to X, right? And if W is a part of our null space, then TW would be equal to 0, which implies that X is equal to 0. So to show that X is equal to 0, we can simply show that W is part of our null space. Okay. Recall that we also have the function T2. T2 is simply the composition of T with itself, and T2 is a function from V to V. How do we know this? Well, we know that T is a function from V to V, and by the rules of function composition, we can see that T of T is simply this function, right? So we have this function T of T, and this is a linear transformation as well. So also W is in V, right? So T2 maps W to some element. We know that. Now let's use the rules of function composition to simplify this equation, and we get this T of TW, and we know that T of TW is just X. So what we have is T, and T of W is just X. So T of X, and T of X we know is equal to 0. So in the end what we have is T2W. We get T2W is equal to 0. So this means that W is in the null space of T2. Where do we go from here? Well, recall that we wanted to show that X is equal to 0. And showing that X is equal to 0 is the same as showing that W is in the null space of T. We already explained why that is the case. So we've deduced that W is in NT, is in the null space of NT2. Can I use this fact to deduce that W is in the null space of T? Well, how do I do that? So let's assume that NT, that the null space of T, I need to stop calling this NT. Let's assume that the null space of T2 is a subset of the null space of T. We've already deduced that W is in the null space of T2, and this assumption would imply that W is therefore in the null space of T. W being in the null space of T means TW equals 0, but we also know that TW is equal to X, right? That's what we wrote here. Therefore X is equal to 0. And since X is equal to 0, we've completed our proof that if X is in RT intersection NT, then X is equal to 0, which means that this entire thing is equal to the set containing 0. Now here's the thing. How do we prove this part? We can't just assume this and write down a proof, right? Gap in this proof right now is this part, this assumption that we made right here, that the null space of T2 is a subset of NT. Hopefully you guys can see how this assumption leads to the result that X is equal to 0. And since we can see that this result leads to this conclusion that we want, we can simply proceed with proving this part. In fact, we're going to prove a much stronger result. We're going to prove that NT2 is in fact the same as NT. Of course, given these initial conditions that the rank of T is the same as the rank of T2 and T is a linear transformation from V to V. So given these conditions, we can show that the null space of T2 is in fact equal to the null space of T. And by the definition of equality, this tells us that NT2 is a subset of NT, and we've already seen how this statement leads to XC being equal to 0, which is what we want. Okay, so now let's prove this result, that NT2 is equal to the null space of T. So first we're going to show that NT is a subset of NT2. Okay, and then we're going to show that NT2 is a subset of NT, and then with both of those things shown, we have that NT2 is equal to the null space of T. So assume that U is some element in the null space of T. Now this means that T of U is equal to 0, and also U is in V, right? Because our linear transformation is from V to V. The null space of T is a subspace of V. So any element in the null space of T is also an element in V. Therefore U is in V. So you'll see why that's important in just a second. So T of U is equal to 0, and T of U is, of course, T of U is in V. Therefore this operation, or rather T composed T of U, is defined, right? Therefore T to U is defined, and T of U, this part, is 0. So we have T of 0, and T is a linear transform, which means that T of 0 is equal to 0. Okay, good. So we have T to U is equal to 0, which means that U is in the null space of T2. So U being in the null space of T2 implies that U is a element of the null space of NT2. Therefore the null space of T is a subset of the null space of T2. This result has been shown. We'll now show that NT2 is a subset of NT, and this result is a bit more involved. It requires some more work. Okay, so again we proceed by the same argumentation. Let U be some element in the null space of T2. This means T2 of U is equal to 0. T2 of U is, of course, equal to T of U. And keep in mind that we want to show that U is a part of the null space of T. This is what we want to show. So in other words, we want to show that T of U is equal to 0. Okay. So from this equation we can reduce, since T of this element is equal to 0, we can deduce from this that T of U is in the null space of T. And if this seems a bit abstract, then I'll make this a bit easier to understand. So think about what this really is, this entire expression. So this is T of some element. We call this element, let's give it some fancy name, xi. And T of xi is equal to 0. Now let xi be equal to T of U, and it's a bit easier to see why T of U is in the null space of T, when instead of T of U we write something like xi. Alright, so this expression means that xi is in the null space of T, and xi is nothing but T of U. So T of U is in the null space of T. Of course, I expect most of you would be familiar with this this much abstraction. So, but for those of you who aren't, just want to explain that part. Okay. So T of u is an NT. Now we want to show that T of u is equal to 0. How do we do that? Well, we're finally going to use the assumption that we have in the question, which is rank of T equal to rank of T2. Notice that, okay, so T of V is a linear transformation, and by the dimension theorem, we know that the rank of T plus the nullity of T is equal to the dimension of V, which means nullity, I'm just going to write that down, nullity of T plus rank of T is equal to the dimension of V, right? Now, T composed T is also a linear transform from V to V, and the rank nullity theorem or the dimension theorem applies to this linear transform as well. So the nullity of T2 is equal the nullity of T2 plus the rank of T2 is equal to the dimension of V. Now we can equate these two and we get nullity of T plus rank of T is equal to the nullity of T2 plus the rank of T2. And by the assumption we made at the start, Jesus, I need to learn straighter lines, okay. By the assumption we made at the start, that the rank of T is equal to rank of T2, we can cancel these terms out since they're since they're equal, and we have nullity of T is equal to the nullity of T2. Now what does this mean? Well, the nullity of T simply means, what does it mean? I forgot. Give me a second. Nullity of T simply means the dimension of the null space of T is equal to the dimension of the null space of T2. What does this mean? Well, it simply means that the basis of NT has the same number of elements as the basis of NT2! Exclamation mark. And we're going to use this to show that NT2 is a subset of NT. So let's call it beta. Let's just call it B. I'm going to use beta actually. Let beta, for the Americans listening, beta. Let beta NT denote the basis of the null space T, and let's say that these guys contain, so let's say that their dimension is equal to n. We're dealing with finite dimensional vector spaces, so of course the null space's dimension would be an integer, like a finite number. So let's say that they have n elements. The basis of NT and NT2 have n number of elements. So we have V1, V2, all the way up till Vn. Also, NT is a subset of V, and NT2 is also a subset of V. So the elements in the basis of these two sets, so V1, V2, Vn, all the way till Vn is one of the bases for NT. All of these elements are also part of V. Okay, keep that in mind. So let this be the basis for NT, and let beta NT2 denote a basis for NT2. And I'm going to label, and it has n elements. I'm going to denote them with W's, Wn. Okay, good. Now, okay, where do we go from here? Now the bases of NT and NT2 have the same number of elements. We've already established that. And now the basis of NT, this is the basis of NT. All the elements in the basis of NT will also be in the null space. Will also be in NT, right? So V1, V2, all of these elements are in the null space of T. We've already established that the null space of T is a subset of the null space of T2. Right? We established that somewhere here. Yeah. This means that V1, V2, Vn, all of these elements are in NT2 as well. Moreover, V1, V2, Vn, all the way till Vn, this is a basis for NT, which means that this set is linearly independent. It's linearly independent. We see that this set has n elements and that it's linearly independent, and that all of these elements are part of NT2. And what's the dimension of NT2? Well, the dimension of NT2 is just n. We've shown that earlier. So this set is a linearly independent subset of NT2 that contains n elements. Therefore, by some theorem in the book, I can't remember which one, but I'll just recall it in a second. But by that theorem, V1, V2, Vn, the set is a basis for NT2, right? And this is just the null space basis for the null space T. NT. And this is also a basis for NT2. So NT2 and NT have a basis in common, which means that NT is equal to NT2. Why? Because the span of this basis will be equal to NT, and since this set is also a basis for NT2, its span will equal to NT2. So we have span of this equal to this NT and equal to NT2, which means null space of T equals null space of T2, which means that the null space of T2 is a subset of the null space of T. Now, why did we want to prove this in the first place? Well, because of this part. Where is that part? Okay. Once we've shown that NT2 is a subset of NT, or in fact we've proven a much stronger result that NT2 is equal to NT, once we have that result, we can use it to deduce that x is equal to 0. And why did we want to deduce x is equal to 0? We wanted to deduce because we're trying to prove that RT intersection NT is equal to set 0. And the result that I use right here, that to show that V1, V2, all the way till Vn is in fact a basis for NT2. So here's the result. Nice. Here is the result. I'm going to paste here. Yeah. Here's the result that I used to show that NT2 and NT have the same basis. this one in particular. So the basis set, so in this case our V, quote unquote V, is just NT2, and the linearly independent subset we have in question is V1, V2 all the way till Vn. This set is a linearly independent subset of NT2 and it contains exactly n vectors, and the dimension of NT2 is n, which means any basis for NT2 will have n vectors. So this set is a basis for NT2, and of course this set is also basis for NT, which means that NT2 is equal to NT. Now just to recap the idea of our proof, because the details you can rewind and go through them again, but just to recall the idea of our proof. So this is what we did. We have some linear transformation T from V to V. We've been given that the rank of T is equal to the rank of T2. We want to show that RT intersection NT is equal to the zero set, is equal to the set containing 0. Now, the idea of a proof was we let X equal to be some element in RT intersection NT, which means X is an RT and in the null space of T. This part tells us that there exists some element W such that it's equal to X and the T of X is equal to 0. And all this while we want to deduce that X is equal to 0. So after this we show that since NT, we consider the equation T2 of W, which is just T composed dx, T of X is just 0, and we get 0. So we have T2 of W equal to 0, and X being equal to 0 is the same as, we then established that X being equal to 0 is the same as showing that the W is in the null space of T. Then we go through this computation and we get this equation, and after getting this equation that T2 W is equal to 0, we note that W must be in the null space of T2. We then prove that NT2 is equal to NT. We use this result, and then since NT2 is equal to NT, any element in NT2 will also be in NT, and we get the result that we wanted. So from this it follows that T of W equal to 0, and T of W is just X, so X is equal to 0, which is what we wanted. So this was the general idea of the proof. I'm going to prove this part, deduce that V is the direct sum of RT and NT later, but for now this is we're going to try to work on this proof.